I'm Roald Hoffmann. I'm a professor at Cornell University. I have a special connection to the Nanothread project. In part, it is through John Badding, and we'll explore that. And part it is through the material. John had a connection to Cornell. Both he and his brother had spent some time there, but also I remember John coming over to our research group and talking to us about some early studies that he had done, which involved the graphite to diamond interconversion and the mechanism of that reaction under pressure. As you know, just a little bit of pressure, a few gigapascals, is enough to shift the equilibrium way over toward diamond. That's why diamonds are made in the mantle. Graphite doesn't have a chance at elevated pressure. We had independently explored benzene under pressure, and there were two directions that we took. We meant myself and Neil Ashcroft, a leading physicist with whom I developed a collaboration only in 2007, 2008 on materials at high pressure and on bonding at high pressure. And as part of that collaboration, Xiaodong Wen explored what happens to benzene under pressure. And we explored it pretty randomly. We were wondering whether a metallic phase would occur as one explored it. And there were two things that came out of that, which I was fortunate enough to pursue and which played a role in things we did later. That was around 2010. So that was about 11 years ago. And one thing was that eventually we found that the global minimum for benzene when it was compressed at very high pressure was graphene, was a saturated polymer. Now, I didn't connect that up to nanothreads at all, but it planted the important seed in my mind that despite the aromaticity of benzene and the special stability of the molecule, thermodynamically, there was a driving force to form single bonds from multiple bonds. The second thing that came out, and it came out from essentially the program at some very high pressure, around 100 gigapascals, giving an array of one-dimensional polymers. And that is one of the all-saturated nanothreads that we know, that we have talked about. It's the one where the benzene rings are connected to each other with 4 bonds between one benzene ring and the next, and then 2 to the next one, and then alternating 4 and 2. This came out eventually in the enumeration that Crespi and co-workers did to be not the most stable one, but it opened up. It was a polymer of benzene, a saturated polymer. And we noted it. I loved its picture. I didn't think of the simpler one. I didn't know of Vin's earlier work, which came, as he has related, from nanotube work and from thinking about how to stabilize very thin nanotubes by adding hydrogens to them. It's been a very interesting time working through chemistry and seeing the connections fall into place between different parts of chemistry, uh, different things happening in one part like solid state chemistry and materials under high pressure, and relating that to other chemistry that I have done. The work on the benzene nanothreads, for instance, connected up to some work we did on just dimerization of benzene. I could uh, eventually see the connection, but when I did that work, it had started from something else, and that is when we were looking actually at calculations at benzene under pressure, we found some unusual structures, which neither I nor anyone had thought of, certain stereoisomers of two benzenes coming together. And we did a paper on that, and I was very happy with that work. But that work somehow then related to the benzene polymers that we are doing in the nanothread project. I used to think, like anyone taking an organic course, that benzene was the cat's pajamas. I mean, that there was nothing more typical of organic chemistry and stable. Now, of course, there are a number of ways that I was wrong even then. What's interesting about benzene is not so much its stability, but the fact that it retains its structure as it undergoes its reactions. So the kind of things that you learn in a beginning organic course about electrophilic and nucleophilic reactions on benzene, that you can make a substituted benzene, that you can make phenol, or so many things are, in our experience, are based on substituted benzenes, testifying to the stability of the skeleton. But if you think about it, they also testify to the fact that benzene is not helium. It is reactive, but its reactivity can be controlled and the structure maintained. For instance, I knew that benzene has a positive heat of formation. Now, what that means is that the reaction of carbon, graphite, or diamond, they're about the same, with hydrogen to give benzene is uphill thermodynamically. That is not true for methane, ethane, many other hydrocarbons that have single bonds in them. And here I thought benzene with aromaticity, that this was very, very stable. But it turns out that that positive heat of formation is a sign that there is a way to go downhill from benzene. And the nanothreads that you guys have made are one of the ways to go downhill. That's part of the driving force, where you're using pressure to probe that desire, if we can talk about anthropomorphically, of the benzene molecule to go to something else. But the activation energies are very big for the reactions out of it because of the aromaticity. And as we constructed with Bo Chen some idea of the thermochemistry involved in going from benzene to dimers to one-dimensional polymers, the nanothreads, to then two-dimensional, three-dimensional structures. And we saw that it was first uphill and then downhill. That was a real revelation, and also connection to something else we've done. In between, and totally unmotivated by the nanothread work, we had looked at the dimers of benzene. And they are all uphill from benzene because, let's see, the story thermodynamically overall is like this. To go from benzene to make all saturated bonds in the nanothreads or graphene is downhill enthalpically. It's not going to happen very easily entropically, but because you have to arrange the molecules, and that's what the solid gives you, is a preordained arrangement of the molecules in each other. But to go, if you go by stages, what we now call, after the paper that Bu Chen did, in which we plotted out a roadmap for going from benzene to the all saturated or stage 6 nanothreads, when we go through partially unsaturated nanothreads, eventually you go downhill to the all saturated ones. The all saturated ones are enthalpically more stable than benzene. But if you form the dimer, that's uphill still, because you have ruined the aromaticity of 2 benzene molecules. And that is probably a loss of about 60 kilocalories or so there. And then you've gone downhill by converting, by forming 2 new bonds or 4 new bonds. And forming sigma bonds from pi bonds is downhill enthalpically, energetically. So overall, it's actually the dimers are uphill. The most stable benzene dimer is some 40 kilocalories per mole less stable than 2 benzenes. This was a paper from 2012. So this is 3 years before the Fitzgibbons experiment. And there's a title, Jailbreaking Benzene Dimers. So there's benzene at 0, 2 benzenes. And then there are the black bars are the known, at that time, known dimers of benzene. You see the molecule number 3 is the lowest enthalpy dimer. It's the result of a Diels-Alder reaction of one benzene to another one. And there are some other dimers. The black bars are the known or hypothetically suggested benzene dimers. For instance, the highest energy one, the one that's called the 6-prismane, is just forming 6 bonds, which is crazy. And that's very strained. And that's 120 kilocalories above 2 benzenes, whereas the lowest dimer, the Diels-Alder one, you should be seeing my pointer, is that one. So in this paper, we came out of our calculations were 4 other dimers, which you see in molecules 4, 5, 7, and 8, and or rather 5, 6, 7, and 8. And they are molecules in which, in the 4-membered ring, if you look at right, the 2, what were the benzene rings, come off at a unusual stereochemistry relative to the simple 2+2 dimers. One of the things that I think that is good about this paper is we didn't just suggest these molecules, we went on to look at what they might do. So we studied reactions of the dimers going on to further polymers. You can see the relationship to what we're doing on the nanothreads. And we found that there are not too large barriers to going on, but the free energy change is going to be positive because there is an entropy factor in going on. And again, in a rigid environment, it might. Anyway, you can see here us thinking in 2012 about benzene oligomerization, if not polymerization. Then we embarked on the major project that Boo did in his enumeration of the possible stage 2 and 4 waypoints, which was difficult and instructive. It was difficult because it probed the enumeration problem. It was instructive because we could see how complicated the scheme could be. Meanwhile, as you know, Dirk Trauner had suggested the polytwistane structure from his work on twistane. Again, it's interesting, from an organic chemistry background of making dimers of twistane and trimers, and then thinking perhaps that the polymer was nothing that you could systematically make, but it was interesting that it turns out in the calculations to be by a little bit the most stable structure of these things. Kind of factors that we learn from simple organic chemistry. We learn there are steric and stereoelectronic factors and no molecular orbitals here. The CH groups in the 3,0 structure, they're all eclipsed. And that is a factor mitigating against. And what happens in the polytwistane, maybe there's some angle strain, maybe a little bit. One would have to look at the optimized angles, but the eclipsing is relieved a little bit. If you look at the structure, each CH is slightly twisted relative to the other ones. I think that's enough to add up. Platonic polyhedra, cubes, octahedra, dodecahedra, icosahedra, and symmetrical structures in general have a direct way into our mind or soul. You don't have to tell anyone that a dodecahedron is beautiful. But then you give them the structure of hemoglobin, and you have to teach someone that they should have the courage, or that they should look at the function of hemoglobin and then they'll think it's beautiful. This is not about reality. This is about what's in our minds. Part of it in general is people want the world simple. That scientists are no better than other people. That they will fall for simplicity just as much as anyone else, even when they themselves are responsible for seeing just how complicated the world is.
This video was produced by the Center for Nanothread Chemistry. In an effort to promote an inclusive and equitable research environment, postdocs and graduate students received the opportunity to interview a senior scientist in the center to nurture new professional relationships during an informal chat with guided discussion questions during video production. Their discussion was recorded, edited, and posted to share their advice, experience in science, scientific challenges, and more.